ARRC hybrid rockets with peroxide oxidizer. The Advanced Rocket Research Center, ARRC, has pioneered hybrid rocket motors that pair a solid fuel grain with high-test hydrogen peroxide, HTP, as the liquid oxidizer. By combining the safety and mechanical simplicity of solid rockets with the throttle ability and shutdown capability of liquid systems, ARRC's hybrid peroxide designs aim to bridge the gap between reliable suborbital-sounding rockets and flexible reusable launch vehicles. Principles of hybrid rocket propulsion. A hybrid rocket motor operates on two distinct propellant phases. Solid fuel grain, typically a polymer matrix such as hydroxyl-terminated polybutadiene, HTPB, or paraffin wax, cast into a cylindrical grain with an axial port. Liquid oxidizer injected into the combustion chamber under pressure, reacts on the surface of the fuel grain to generate thrust. Key advantages of this scheme include throttle and restart capability. Liquid flow can be modulated or shut off, permitting precise thrust control. Safety and simplicity. Absence of a fully liquid bipropellant system reduces plumbing and leak hazards. Cost efficiency. Solid grains are inexpensive to manufacture. Peroxide oxidizer is storable at moderate pressures and temperatures. High-test peroxide, typically 85 to 98% H2O2, serves as the oxidizer in ARRC's hybrid designs. Catalytic decomposition. Before injection, peroxide passes over a catalyst bed, silver or alumina, to produce hot steam and oxygen, improving combustion stability. Advantages: non-cryogenic storage. Low toxicity compared with nitric acid or hydrazine. Simple pressurization, gas or pump fed. ARRC's research has yielded breakthroughs in hybrid peroxide motor design. Advanced injector geometry. Optimized swirl injectors ensure uniform oxidizer distribution along the fuel grain for consistent regression rates. Regenerative cooling channels. Peroxide is circulated around the combustion chamber walls pre-decomposition, providing thermal protection and preheating. Modular grain architecture. Interchangeable solid fuel segments allow rapid reconfiguration of burn duration and thrust profile. Integrated health monitoring. Fiber optic pressure and temperature sensors embedded in the grain provide real-time combustion diagnostics. Case study: ARRC HPR-5 test stand. During static fire testing of the HPR-5 motor. Chamber pressure, 25 bar. Thrust output, 5 knots, variable throttle 30 to 100%. Burn duration, 60 s per grain assembly. Measured ISP, 260 s. Key lessons learned included the importance of catalyst bed longevity, exceeding 100 cycles, and the management of peroxide decomposition heat to avoid runaway temperatures in the feed system. ARRC's peroxide hybrid rockets are well suited for sounding rocket missions requiring rapid turnaround. Small satellite launch platforms, sub-200 kg payloads. Testbeds for advanced aerobraking and in-flight restart techniques. Future research priorities encompass enhanced ISP, blends of technical peroxide with additives to boost oxygen content. Fully pump-fed systems, turbopump integration for higher chamber pressures. Green propulsion certification, meeting stringent environmental standards for commercial launch sites. By harnessing the controllability of liquid oxidizers and the simplicity of solid fuels, ARRC's hybrid peroxide rocket programs offer a compelling middle ground in propulsion technology. Ongoing innovations in injector design, thermal management, and feed system safety promise to elevate these engines from experimental labs to reliable commercial service vehicles.